Hey guys, it's Grant and I'm back again with another video. And today we're finding the mass of the surface S, where S is the portion of y squared plus z squared equals 4 between x equals 0 and x equals 3 minus z. And the mass density is the distance to the z-axis multiplied by the distance to the yz plane. Alright, so we've got a lot of moving pieces here, so let's just graph the surface and see what we can deduce from that. So, the surface, let's see. So it's y squared plus z squared equals 4. So we need to be careful here. If this was x squared plus y squared equals 4, obviously it'd be a cylinder xy plane going up. This is a cylinder in the yz plane, right? So it's going to look something like that coming out right out of the paper. And it's between x equals 0, which is the yz plane, and x, this plane, x equals 3 minus z. So let's see here. I'm going to redraw this, but ultimately, well, it's going to be when z is 0, x is 3, and when x is 0, z is 3 as well. So it's going to be some kind of plane like that, and that's pretty jumbled. You probably can't see a whole lot from that, so I'm going to redraw it here. And yeah, that's just some plane that goes up. And important to note here, the surface is the portion of y squared plus z squared equals 4. So it's just, this is a cylinder, but it's just the walls of the cylinder. This cylinder has a front and a back, but we're not worried about that. We aren't worried about the front and the back. We're just worried about the sides because it's the portion of this cylinder. So we don't need 3 separate surfaces. We can just reparameterize this. And obviously we need to reparameterize this because we're trying to find the mass of a surface. So what we need to do is find a surface integral. So when we're talking about surface integrals, all it is just, well, I guess the mass here in this case is just a density function, ds, which when you break it down, you need to compose this density function between some parameters, u and v. ds is just the magnitude of the cross product of these partials, or v, excuse me. dA is over some area A, and u and v are the bounds, right? So, or well, u and v are what you are integrating over some area there. Anyways, so we obviously need to reparameterize this. Y squared plus z squared equals 4. So obviously this has radius 2. It's a cylinder. How we would usually do this, if this was x squared, let's say if this was x squared plus y squared equals 4. How would we reparameterize this? Well, this would be easy. This would just be cylindricals, theta and z. And we'd make this 2 cosine theta, 2 sine theta, and z. However, this is y squared plus z squared equals 4. So what we need to do, we don't have x, so what we can do is use x in theta instead of z in theta. There's no z in here and there's no x in here. So we use z here, now we're going to use x here, right? So now, x is just x. Y is the same, 2 sine theta. And z isn't z. Z is taking the place of x. X in this one was 2 cosine theta. So that is why we would use that. It's a little tricky because when we talk about cylindricals, we usually mean the 3 parameters are r, theta, and z. We're kind of mix and match them a little bit. We're using x and theta in this one. So that's what we're doing. And so, obviously, we'll find the partials in a second. Actually, we'll do it right now. Partial with respect to x, well, that's just 1, 0, 0. And the partial with respect to theta, that's 0, 2 cosine theta, negative 2 sine theta. All right, now let's find a cross product here. Rx cross r theta equals ijk, and it's 1, 0, 0, 0, 2 cosine theta, negative 2 sine theta, excuse me. So this will ultimately be I. That's 0 minus 0 minus j, which is going to be minus 2 sine theta minus 0 plus k, which is 2 cosine theta minus 0. So this is ultimately going to be, scoot the paper down a bit. This is ultimately going to be, what, 0. This is going to be minus plus. This is going to be plus 2 sine theta and 2 cosine theta. So we need the magnitude of this, so that's just the square root of all the components squared. 0 squared plus, that's going to be 4 sine squared theta plus 4 cosine squared theta. All right, well, this is easy. 0 is 0. And this, we can remember our trig identities. Sine squared theta plus cosine squared theta is 1, so we can factor out a 4. Sine squared plus cosine squared theta. This will ultimately be 1. So this is just 4 times 1, which is 4. Square root of 4, that's just 2. So the magnitude of this cross product is 2. All right, magnitude of that cross product is 2. So that's going to go, again, remember, that's going to be that part. That's going to be 2. Now we need to find the density. We said, well, this is a little tricky here. It says the density is the distance to the distance. It's the distance to the z-axis multiplied by the distance to the yz plane. So how do we find the distance to the z-axis? Well, let's see. Let's say we just had a point in space. Point in space, I don't know, x, y, z. How will we find its distance here to the z-axis? This point would be 0, 0, z. Well, they have the same z coordinates. How will we do this? Well, we just do square root, and we just use the distance formula. It would be z minus z squared, x minus 0 squared, y minus 0 squared. So this is ultimately going to be x squared plus y squared, right? X minus 0 is x, y minus 0 is y, z minus z is 0. So this is square root of x squared minus y squared, which is ultimately square root of r squared. Remember, r is just, r squared is x squared plus y squared. Square root of r squared is r. And it's not plus or minus r because we know r is positive. We know r is positive. Well, in this case, what's r? This is tricky. We can't just put r into our integral because we need it to be in terms of x and theta. Well, that's fine. So what we do, we think about it, right? This is a cylinder. This is the walls of the cylinder. We already said r is 2. So r, in this case, is 2. So it's 2 multiplied by the distance to the yz plane. Well, how do we find the distance to the yz plane? We can use a similar process as this. So we have a point in space, again, x, y, z. How do we find its distance to the yz plane, which again is going to have 0, yz, or excuse me, yeah, its x coordinate would be 0, yz. Its x coordinate would be 0. Because it's in the yz plane. So yeah, it's just the square root, x minus 0 squared, plus, again, these y's are going to cancel, and these z's are going to cancel as well. So it's just going to be the square root of x squared, which is just x. So the distance to the yz plane is just x. And this makes sense, right? If I asked you how far away, and I'm running out of paper here, let me get another one. It should make sense to you that the distance to the yz plane is just x, because if I asked you how far away is 231 from the yz plane, well, it's 2 away. It's 2 away. If we draw this out, we could figure out a point there. It's whatever its x coordinate is away from the yz plane, so it's just 2. So that's why it's x. Okay, so our density still is 2. Remember, our density is distance to the z-axis multiplied by the distance to the yz plane. Cool. So this is just 2x, right? We already said the distance to the z-axis is always 2. Distance to the z-axis is always 2. Distance to the yz plane is x. So that is 2x. That's our density function. Density function. All right, so now we're ready to kind of integrate. So we have mass equals, again, remember density function, ds. Our density function here is 2x times the magnitude of the cross product. Remember, magnitude of the cross product. We found that to be 2 times 2. And we're going to go with respect to x here. Okay, now we need to figure out our bounds. Well, it's between x equals 0 and x minus 3. X equals 3 minus z. We obviously can't do that. We can't do 3 minus z. Well, what's z in our... And when we reparameterize this, z is just 2 cosine theta. So this is ultimately just going to be 3 minus 2 cosine theta is going to be our bound. And our theta, we're going around the whole circle. We're going around the whole circle. So it should be 0 to 2 pi.